Section 6.2, volumes using discs and washers. Okay. Section 6.2 and 6.3 both are sections involving volume using different techniques. I'm just going to focus here on section 6.2, finding volumes with what we call the disc method and the washer method. All right, so an extension of what we've already done with area, finding the area of a region under a curve or between two curves. And here we're going to take it into a three-dimensional shape. Right? And let's find the volume of a region defined by a curve, but in a three-dimensional sense. We'll talk about how that happens. All right, so first we'll start with the definition. Now the definition here is a little bit kind of weird sounding, but I'll clarify what exactly this means. But we're going to let S be a solid that lies between the lines x equals a and x equals b. And we're going to take a cross-sectional area of that solid in the plane p sub x through x and perpendicular to the x-axis. And if the area is a of x, a is a continuous function. There's our good old continuity as usual. Then we can calculate the volume as follows. Now what all this is saying is, if I have a solid, a region, bounded by the vertical lines or the planes x equals a and x equals b, and we look at a cross-sectional slice of that solid. In other words, we're going to slice this thing perpendicular to the x-axis. And we're going to define the area of that slice of that region having the formula a of x, whatever a happens to be. Right? It's a function of x. And then if you take the cross-sections, each of which has an area, and they're going to have a thickness, depending upon how thick your slice is. And so I can calculate then the volume of each of those slices by taking the area of the slice times the thickness. And then if you add up all of those areas, you end up with the volume. Now it's the same kind of idea that we did for finding area under a curve using rectangles. And we defined the rectangles, and we took the height of the rectangle defined by the function, and then the width, which was delta x. And then we added the areas of all of the rectangles, and we got the area under the curve. In this case, we're calculating the volume of a slice by taking the area of the region times its thickness, so now it's three-dimensional. So each slice has a volume, and then if we add all those volumes together, we get the volume of the entire solid. All right, now don't put too much into the limit of some things. We're not going to rehash that again. But eventually that's what leads us to our integral. All right, so in other words, to find the volume of a solid whose area, or the area of the slice of the solid, can be calculated using some formula a of x. And then we can find the volume by taking the integral from a to b of that area function dx, right? Because remember, dx is delta x, that's your thickness. Okay. And then I refer to a cylinder below that, so I'm going to kind of use that as a starting point for this. So think about a perfect right cylinder. All right, so let me just kind of clarify what this definition is talking about. Then I have the blue line, which is representing the x-axis. So I have this three-dimensional cylinder, and the x-axis is poking right through the middle of this thing. Think of it like a paper towel roll or a toilet paper roll or something like that, right? But let's make it solid. And then what we're doing is, so we want to find the volume of this cylinder. So what we're saying is, let's take a slice of this thing. Let's slice it perpendicular to the x-axis. So I'm going to cut off a piece. Or maybe you can think of this like a vegetable, like a cucumber, right? And you're slicing a cucumber. Right? And so you slice it, and you slice it, right? And you continue to slice off pieces of cucumber. Now each slice that you make comes out looking like this, right? So we're taking a perfectly round cylinder, so cucumber is round. But each slice is a circle. Right? Now it's going to have some thickness to it depending upon how thick the slice. But I can calculate the area of this thing. Again, my x-axis is running right there through the center. It has a radius. And I can calculate the area of this by using the area formula for a circle, right? Pi r squared. Now, if this happens to be a perfect cylinder, like this one is, and every slice has exactly the same area, then that becomes a constant, right? In other words, whatever the radius of this thing is, every single slice is going to have exactly the same area, so that value then becomes a constant. And how do you calculate, or, yeah, I guess I'll ask it that way. How do we find the integral of a constant? That was one of our rules for integration, or properties of the integral. If I integrate a constant, then it's simply the constant times the difference in its limits of integration. Right? Its upper limit minus its lower limit. In other words, if the area of this region, right, is a constant value, and I know the height or the length of this cylinder, then I can take the area of this region, maybe call it the area of the base, times the height of the cylinder, and you've got its volume. Right? It was one of our basic properties of integrals. Now, again, it's not going to be the main player here, but it's just kind of introduced this whole idea. The bottom line is, I'm taking a slice, I'm slicing this thing perpendicular to the x-axis, right? And since each slice is a perfect circle, then I can calculate the area of each slice, and in the case that it's a constant, then I can take whatever that area is and simply multiply it by the length of our cylinder, and I've got the volume. Okay. Now, the problem is, what if the area of each of our slices is not a constant? Right? What if it changes? Okay. So this is more of what I'm interested in. Kind of a little intro there. Not a very good intro, but a little intro nonetheless. But here's the type of situation we're more interested in. Right? But it's very similar to what we've just done above, because we're going to take a curve. In this case, it's the curve defined by y equals square root of x. And then we're going to spin this curve around the x-axis. Right? So just rotate it this way, to where it ends up forming a three-dimensional shape. Now we're going to take it to be a solid. Kind of think of that, it would kind of look like a bowl, right? If I just took it and spun it around the x-axis, you end up with this bowl-looking thing. But we're going to make it a solid. Right? It's not empty, it's a solid. And we want to figure out what the volume of this thing is. Right? How much material would I need to construct that solid region? Right? But again, if you think about it in terms of what we just said with the cylinder, let me try this. So if I take that curve y equals x squared, and in this case we're asked to look at that curve from what? 0 to 1. So I'm only going from 0 to 1. And then, like we said, we spin it around the x-axis so that I end up with this three-dimensional solid, right? Now, to find the volume of this thing, we're going to do the same thing we did above with the areas, right? So we're going to slice it, and slice it, and slice it, and slice it. But what's the difference, right? Here, each of those slices is still a circle, notice. So there is something similar in this case. But the radius of the circle changes depending upon where you slice, right? That slice that you make out here at this part is going to have a radius that's larger than the slice that you make down there. So the radius is changing. So now when we define our function a of x, which is the area of each of our slice, now it is specifically a function of x, in that depending upon where you are along the x-axis, your radius is different, right? So now we've got an actual function that's going to have to be used to determine the area where the radius is changing as you move from 0 to 1 in this case. Okay? But otherwise, the idea is still the same. I'm still taking a bunch of slices, and I'm stacking those slices from left to right, from 0 to 1. Each slice has a volume. It's the area of the slice times its thickness, which is good old delta x or dx. Okay? And then if I take the integral, right, that limit of sums, as the sum of a sub x goes from 1 to n, or 1 to, as n approaches infinity, then I would get the volume of that solid. Right? Again, it's exactly the same idea that we use the rectangles to find the area under the curve. Here, we're using the area of the slice, which has to be a circle because we're spinning that curve around the x-axis. It's going to be a circular shape anytime you slice it. All right, and that's how we're going to form our solids that we're going to work with. We're going to take a function, we're going to take a curve defined by some function, and we're going to spin it around some axis, whether it's the x-axis, maybe the y-axis, or some other horizontal or vertical axis. So we know that it's going to always form, or that each of its cross sections is going to form a circle. So we have a formula for calculating the area of a circle, pi times the radius squared. The only thing I then have to do is determine how do you calculate the radius, depending upon where you are on the curve. But look, that's not as difficult as it may seem. Because if I take a circle, take a cross section here, right, it's going to give me a circle. What's the radius? The radius of that circle is going to be this distance, right, because this is the center of the circle. Well, what's that distance? It's that. Now, I'm going to ask you a simple question first, and keep this in mind, because this is going to bail you out of a lot of this going forward. When I say measure the radius, I'm measuring from the center of the circle to the outer edge of the circle. If you measure, in this case, I'm measuring vertically, right, from the x-axis up. When you measure vertically, you're measuring a y value, right? If you were to measure horizontally, you're measuring an x value, right? Keep that in mind as we go forward and we look at different situations. If I'm measuring my radius vertically, then I'm measuring a y value. And in this case, what is y? Y is square root of x. If I measure horizontally, I'm measuring an x value, okay? So keep that in mind. That's going to come into play here shortly. And since we're defining the area of this as a function of x, then what is, then I've got a of x, in this case, pi r squared, where that radius is defined by our function y equals square root of x. So the radius of that circle, of that slice, would be whatever that y value is, which is square root of x. That's going to be the most important observation that you're going to have to make with these, because otherwise it's a pretty straightforward setup. It's the integral from a to b of the area of the circle, which is pi r squared, times the thickness, which is dx. Your task is going to be to figure out what the radius is. Okay? So that's what leads us to the setup of our integral. And so again, I'm just taking all these slices, they're circular. When we call those cross sections, we don't just call them circles, we call them discs. Okay? So it's a circular disc. That's why we call this the disc method. And the radius of the disc is square root of x, because that is the distance from here to here. Okay? It's a y value, which is square root of x. And so then if I slice, now you're always going to slice perpendicular to your axis of rotation. And so that's why I keep asking about which direction I'm measuring. So if I happen to slice perpendicular to the x-axis, as we did here, then I'm going to measure my radius vertically. If we were to rotate something around the y-axis and then slice perpendicular to the y-axis, then I would be measuring my radius this way, horizontally. Okay? So that's always going to be your main observation. When I measure the radius, am I measuring vertically or horizontally? So if I'm measuring vertically, it's y. If I'm measuring horizontally, it's x. All right, so let me not overcomplicate it before I have to. So bottom line, we're taking the volume of our solid to be the integral from a to b. In this case, the integral from 0 to 1. We're given those as our limits of integration of the area of our slice times its thickness. Now, the area in this case being a circle, pi times the radius squared. Our radius is square root of x. So I've got square root of x squared, which just gives me x. So I simplified that to simply pi x. And so then calculating the volume, a of x is pi x, integral from 0 to 1 of pi x dx. And just like we did with the area in the previous section, I'm just going to be looking for you to set up your integral, and then you can approximate it on the calculator. All right? I mean, this one is easy enough to do an antiderivative of and all that, give me an exact value of pi over 2. But if you just run it through the calculator, give me an approximation, that's fine. Okay. All right, so bottom line, I'll try one more time because I don't think it's coming out clearly or as clear as I'd like it. So I have a solid that's defined by a curve rotated about some axis. To calculate the volume of that solid, I find the area of a cross-section of that solid, which is always going to be found using the area formula for a circle, pi times the radius squared. Your main goal is to define the radius. How do I define the radius of our solid, right, of that cross section? And then we integrate over our interval, whatever that happens to be, of our area, pi r squared dx, and then approximate the interval. Let's try another one. So here I'm looking for the volume of the solid. This one is formed by taking the function y equals natural log of x, y equals ln of x, bounded by y equals 1 and y equals 2, those two horizontal lines, and the vertical line x equals 0, which is your y-axis. This time we're going to rotate it about the y-axis. All right? So here's my region. Here's our curve, y equals ln of x, bounded by y equals 1 and y equals 2, or from y equals 1 to y equals 2, and x equals 0, which is the y-axis. So this is the region that we're interested in. And then we're rotating it about the y-axis this time, right? So we're rotating it this way to form this three-dimensional solid. Okay? And then we're looking for the volume of that thing. Now, like I told you earlier, whatever the axis of rotation is, you're always going to slice perpendicular to your axis of rotation. That way your cross-section is always going to be a circle. And the reason it's always a circle is because you're taking a curve and you're spinning it, right, in a circular fashion around your axis of rotation. So it's always going to be a circle. So then we slice perpendicular to the y-axis in this case, right? So this time my slice is this way. So here I'm looking at a circle. If we're going to say the y-axis is here, and I slice horizontally perpendicular to the y-axis, I need to know the radius of this circle. And this is what I was alluding to earlier. Since I'm slicing this thing perpendicular to the y-axis, then my radius is measured from the y-axis out. That's a horizontal distance. That's an x value. Okay? Now, since we're slicing perpendicular to the y-axis, we are then going to be stacking those slices vertically, right? So in other words, when we integrate, we're integrating this way. We're integrating vertically from what? Y equals 1 to y equals 2. Those are the boundaries, those horizontal lines that we're given. So what does that tell me about my radius then? If I'm going to integrate vertically with respect to y, then I need the radius in terms of y. So the radius is being measured horizontally, which is an x value, but I need that in terms of y so that I can integrate vertically with respect to y. What's our curve? Our curve is y equals natural log of x. Right? That's this curve that defines the boundary of our circle. So then when I'm measuring the distance from here to here, that's an x value, but I need it in terms of y. So we take y equals natural log of x, and I need to solve that for x, basically. I need to know what x is in terms of y. And this goes back to our early kind of review discussion of our log functions and exponentials. Remember, there was that conversion between the log equation and the exponential equation. So y equals natural log of x is equivalent to saying that x equals e to the y. Right? The argument is equal to the base raised to this power. So here is x as a function of y. And that's what I need for my radius, since I am integrating vertically with respect to y, right? So that's kind of, I guess, what complicates this process, right? It's the fact that, yes, I have to define the radius, but I also have to make sure it's defined with respect to the correct or proper variable. And if you're integrating vertically like we're doing here, it needs to be in terms of y. With the previous one, when we were integrating from left to right, we had our radius in terms of x, okay, because we were integrating this way with respect to x. So if you're integrating horizontally, you need your radius in terms of x. If you're integrating vertically, you need your radius in terms of y. And that's about as straightforward as I can put that. So now we have x equals e to the y, so I can replace x with e to the y. There's my radius. Okay. All right, so we're slicing perpendicular to the y-axis because that was our axis of rotation. We get a disk with radius x, but I need that in terms of y because I'm integrating vertically with respect to y. So I'm going to replace x with e to the y. That'll be my radius. So I now have an area that's a function of y. It's pi times the radius squared. Pi times e to the y squared, or e to the 2y. And then I can integrate then from 1 to 2, because those are our horizontal lines, y equals 1 to y equals 2. So there's our integral from 1 to 2 of pi times the radius squared. And then again, you can plug that into your calculator. You don't have to do any of the simplification like I did. Notice I actually did the integration. I had to go through substitution to do it. So, I'm trying to save you a little bit of work with these and not have to go through all the integration techniques. But this was a substitution method that I used to integrate this. So if you want to look at that, kind of gives you another example of integration using that substitution method. Okay. But bottom line, you can take that integral. Once you have the integral, plug it in, and you get approximately 74.16 is what you should get. Okay. Now, each of these first two examples, we formed our solid by taking a single function and rotating it about an axis, the x-axis or the y-axis as we did in this case. And when we took the cross-section, we said the cross-section, we called it a disk. Okay. Because it was a solid. It was a solid circle, so we called it, that's what we refer to that as the disk. Next couple of examples is going to bring into play the washer method. Difference between disks and washers. Notice in this case, I'm looking for the volume of the solid bounded by the curves y equals x and y equals x squared. And we're rotating that about the x-axis. So now we're kind of dealing with the same idea as finding the area between two curves, right? Where we have an upper and lower curve and we took the difference between the two, etc. So here, if I'm looking for the volume of a solid that's enclosed between those two curves, now there's an outer curve and an inner curve, right? So the inner part of this thing is hollow. So if you take those curves, y equals x, which is that nice horizontal line right here, and then I take the curve y equals x squared, which is our parabola. It's not a very good distinction, but try it over here a little bit nicer. All right. So I've got the curve y equals x. Let's try to hit the origin, and then we've got y equals x squared. Right? So these are our two curves, and so we're interested in the region that's bounded by those two curves, and then we're rotating it about the x-axis again. Right? So now when I spin this thing about the x-axis, right, this is passing through the origin, so that's fine. This point, I would need to know that point of intersection, and we could find that easy enough if you set x equal to x squared. I'm not sure if I did it over here or not. But if you set x equal to x squared, right, just like we did before, and get this thing to cooperate with me. Those points of intersection, right, x equals x squared, where is that going to happen? Right? So we could do what? 0 equals x squared minus x. Factor out an x. And I've got x equals 0 and what, x equals 1. Okay. And we already knew the 0 because we could see that from the graph. All right, but anyway, that gives me this other point of intersection, which is at 1. And so when we spin this around the x-axis, now also notice what's the y-coordinate. I'm just trying to be accurate with it. I don't, you don't necessarily have to do what I'm doing here. We do have to know that point of intersection because we have to know, right, what's the interval over which we're integrating. But this happens to be at the point 1, 1, right? Because if I plug 1 into either x or x squared, I'm going to get 1. Because I wanted to draw a nice little picture here. So in other words, when I spin this thing around the x-axis, this point that's at 1, 1 ends up down here at 1, negative 1, right? And so you end up with something that looks like this. Right? And there's our region, right? Because we're spinning it this way. But then the difference between what we've done before and this is, here's the x-axis. I have a inner and outer circle there, right? And the area that we're interested in is this area between the two curves. And then when we spin that thing, we want the volume of the solid formed by that region. But this is what we call a washer, right? There's a hole in the middle, instead of our disk, which was completely solid. So if I want, instead of the area of the whole thing, I only want the area between those two, how am I going to find that area? I think you should be able to tell me that. How about if we just take the area defined by the outer circle and subtract out the area defined by the inner? I'm just going to call it the outer area minus the inner area. And that would give us the area of the washer, and then we could integrate from 0 to 1 using the formula that we find for calculating that particular area. Okay? So we're going to take outer area minus inner area, which means, we said for area, I need to know the radius. So I need to come up with a formula for calculating this radius. We'll call that maybe the outer radius, maybe call it r sub o for the outer radius. And we need to know this inner radius, so I can calculate the area of that inner circle. So maybe I'll call that r sub I. So I need to know which function is defining the outer radius. When I slice this thing perpendicular to the x-axis, the outer curve is this one, which is y equals x. Now, I'm measuring, or I'm going to be integrating along the x-axis, right? I'm integrating this way because I'm slicing perpendicular to the x-axis. So remember what we said, if we're going to integrate horizontally, then I need my radius as a function of x. All right, so the outer radius is, or comes from the curve y equals x. I need it in terms of x because I'm integrating horizontally. I'm integrating along the x-axis. The inner radius comes from the other curve, which is x squared. So my inner radius comes from this curve. Here's my inner radius, x squared. Again, I'm integrating horizontally. So I'm measuring the radius vertically, right? It's a y value. But since I'm integrating horizontally, I need it in terms of x. So that's always the trickiest part with these. Once you come to grips with that, it's pretty straightforward. I mean, the integral isn't the deal. It's setting it up. Right? All right, so use what we just said. Since I have an outer area and I need to take out that inner area, all right? So we're going to call this a washer. All right. And let's see. We've got an inner radius, y equals x squared. That washer has an outer radius of y equals x. And so we're going to take the area of the washer to be that outer area, or the area of the outer circle, minus the area of the inner circle. Okay. So then our area function, a of x, area of the outer circle, pi times the radius squared, minus the area of the inner circle, pi times the radius squared, right? Radius is x squared, squared. And then all I did from there is I just rewrote it as, factored out the pi, and I've got pi times x squared minus x to the fourth, right? X squared squared. And there's our area function. And once we have that, as I said, the integral is not the issue. So I'm integrating from 0 to 1, because those are our x values for the points of intersection, and we're integrating along the x-axis. So integral from 0 to 1 of our area function, which is, again, the area of the outer minus the area of the inner. Okay. I gave you the exact value, or again, you can plug that into your calculator and you get approximately 0.4189. But that's the idea. I mean, so the only thing from this point forward is, like I said, how do you define the radius? Now, all of those have been done by spinning it or rotating our region around either the x-axis or the y-axis. So it was a little bit straightforward as far as how we measured the radius. It was directly defined by the curve. Here's something a little bit different in number 4. I've got the curve again, y equals x and y equals x squared, so the same two that we just dealt with. But this time we're going to spin it about the line y equals 2. So around that horizontal line, y equals 2, and so we're spinning it this way. All right, so again, I'm going to end up with a washer, right, because we're looking at that region that's bounded by those two curves, so this little region, and we spin it up this way. So our cross section, when we slice it this way, I'm slicing it that way because that's perpendicular to my axis of rotation. Right, we're still spinning it around a horizontal line, even though it's not the x-axis, it's a horizontal line, so I'm always going to slice perpendicular to the axis of rotation. So then I get a washer that looks something like that. And again, you've got an inner and an outer radius. Right, so to calculate the area of this washer, I need to find the area of the outer circle. What is the radius of the outer circle? What is the distance from our axis of rotation to that outer curve? Okay? Now, here's where you're going to have to be observant. I mean, there's no memorization here. You have to look at the relationship between your curves and your axis of rotation, and I want to measure that distance. Now look, I'm measuring my radius in this case is a vertical distance, right? So that's a y value. But since I am slicing perpendicular to the x-axis, then I'm going to be integrating with respect to x, right? I'm going to be integrating this way. So I need the radius in terms of x. So I need to define it y as a function of x, because this is a y value. I'm measuring it vertical. What is that distance, or what is that value? Well, we know the distance from here to here is 2, because that's the line y equals 2, right? So that distance is 2. And then if I subtract out this distance, that would give me the radius of that outer circle. Well, what's that distance? Well, that's going to be defined by that outer curve, which is x squared. So that's where I come up with this outer radius. It's 2, which is the distance from here to here, minus this distance, which is y equals x squared. That leaves me with that distance, which is the radius of that outer circle. Right? So it's a little bit more involved. It's a little bit trickier, but it's all done from observation. So then we need the inner radius. We need the radius of the inner circle. So again, I'm looking at the distance from here to here as 2. And then if I subtract out, try that again. If I subtract out this, come on. Subtract out that distance, we'll get it eventually. Then that would give me my inner radius, right? So that distance is given by this curve, right? That's that inner curve, which is y equals x. That's that inner circle. So similar to the outer circle, right? The inner circle is defined by the curve y equals x. So if I take this distance, which is 2, subtract out this distance, which is x, then I've got the inner radius, 2 minus x. Yeah, it's not it's not an easy thing, but again, it comes back to observation. You have to really observe, the formation of the region, right, and how that radius is measured. Okay, so as I said, there's no magic pill for this one for sure. It all depends on where your axis of rotation is, and then you measure the radius from the axis of rotation to the curve, and then how do I define that distance? Okay. So again, that's the hard part. The rest of it is straightforward because the area of that washer now is the outer area minus the inner area, right? So the area of the outer circle minus the area of the inner circle, pi r squared in each case. We said the outer circle had a radius of 2 minus x squared, so pi r squared for the outer circle. And we said the radius of the inner circle was 2 minus x, pi r squared for the inner circle. Right. And again, I just rewrote them by factoring out the pi. I don't care which way you put that in there. If you put this whole thing as your integrand, that's fine. I mean, area of the outer minus area of the inner, that's your integrand. Whatever you want to do with that to simplify it before you plug it into the calculator, that's completely up to you. And then again, we're going from 0 to 1 because those are our points of intersection, right? We're still dealing with the same two curves, so those points of intersection, and we are integrating along the x-axis, right? So from 0 to 1. And so there's our integral from 0 to 1 of the outer area minus inner area. And that'll give us the volume, which is approximately 1.6755. Little more of a challenge. Just a quick little summary, just to kind of, the two different processes, discs versus washers, right? If the cross section is a disc, then the area is simply pi times the radius squared. And if the cross section is a washer, which means we've defined our region by two curves instead of one, then the area is the outer area minus the inner area, or pi times the outer radius squared minus pi times the inner radius squared. Or you could even factor out the pi and say pi times outer radius squared minus inner radius squared. Right? Either way you want to do that. I have one more example for you, just to make your head hurt. All right, so in this case, again, I'm going to rotate around a different axis. So I've got the curves y equals x squared. I'm using those same two. This time we're going to rotate about the line x equals -1. See if we can make heads or tails of this one. Right. So here's the line x equals -1. So it's a vertical line that we are rotating around this time, right? And so we're rotating it this way. And so those cross sections are going to be sliced perpendicular to that vertical line. So cross section is going to be a horizontal cross section. What does that mean in terms of my radius? That means my radius has to be measured from here to there. All right. Here's the line over to the right. And then my radius has to be defined this way, from that axis of rotation to the curve. And since we're measuring the radius this way, that's an x value. But we're going to be integrating this way. We're going to be stacking this way. So we're integrating with respect to y, which means I need the radius in terms of y. That's what I mean by the direction. So if I look at my diagram, the inner radius is defined by that curve y equals x. This guy. But I need that radius in terms of y. Because I'm integrating vertically, I need to integrate with respect to y. So yes, y equals x, but I need to use x equals y. Here's my radius. And then the same thing with the outer radius. All right, so the outer radius going from that axis of rotation to the outer circle, which is defined by y equals x squared, right? So the radius y equals x squared, but again, I need that in terms of y. So I'm taking y equals x squared in terms of y, so I'm going to solve it for x, right? Because when I'm measuring horizontally, it needs to be an x value, and x is equal to the square root of y. There's your outer radius. Or at least in terms of y. Now, the other part of it is this distance. So I've written those two functions. Let me put it this way. Rewriting x as a function of y, but then I also need that distance, right, from here to here. Let me clear out some of this stuff. Right. So what I've actually defined is not that total distance, but I defined those distances. I also need this distance. So what's the distance from my axis of rotation to the x-axis? All right, it's this distance, which is 1. Not -1, right, because we're talking distance here. And distance is always positive. So that distance is a distance of 1 unit plus whatever those pieces were. And that's what we defined here. Okay. So then my inner radius would be 1 plus our y value. My outer radius would be 1 plus our square root of y. Okay. And again, the 1 is coming from this distance. This is y. This is square root of y. All right. But again, I mean, that's the hard part. Once you have that, then you're plugging everything into your formula, right? Area of the outer circle minus area of the inner circle. So I've got, again, from 0 to 1, because if I go vertically, those points of intersection, remember that was the origin and this was at the point 1, 1. So I'm still integrating from 0 to 1 with respect to y in this case. So integral from 0 to 1, pi times the outer radius squared minus the inner radius squared. This one is what I wanted to do. Pi times the outer radius squared minus pi times the inner radius squared. There's our area function, and then we'll integrate from 0 to 1. And I just rewrote that again by factoring out the pi like I did before. But again, either way, you can put all of this in as your integrand. That's fine, whichever way you prefer. And you would again get pi over 2 if you did an exact evaluation on this, but approximately 1.57, that's fine. Okay. So yeah, it's a little bit trickier with these, because how we define the radius. Now again, what I will probably do to be nice to you on your final is I'll give you one that's rotated about the x-axis or the y-axis, just to make it a little bit easier, because I don't want that to be the issue. Okay. But you will have some of these to look at in your homework, just again kind of play with the idea of calculating that r value, calculating that radius, and how that's done. And yeah, that's just another picture of that thing. So go ahead and show you that one in case you want to make use of that. But that's it for that section. That is section 6.2.